No offense taken. All right. So we're going to talk about what the derivative actually means. And for some of you, I think it's going to come sort of intuitively. For others of you, it might take a little bit of thinking and thought. And here's the thing. If you always remember that the derivative is sort of a fancy name for slope, specifically the slope at a point or the instantaneous rate of change, if you keep that in mind, then you can really remember that what the derivative is representing is a rate of change, an instantaneous rate of change, a change in y over change in x. So if, for example, you had meters and seconds, and we were asking if this is if f of x, that doesn't make sense. If this is f of s, the derivative of f of s would have units of what? What? I didn't hear. What'd you say? Meters per second? Did people say that? Yeah, good. It would be meters per second. The derivative is the rate of change. If we're talking about y values in seconds, the derivative is meters per second. Leibniz would write this like this. He would write the derivative as dm over ds. Do you see how this almost screams at you what we're talking about when we're doing a rate of change?
Yeah, it's the same function.
Yeah. So can you see actually Newton had a notation that was like maybe a little simpler, but Leibniz had a notation that told you what you were finding? Just say yes.
Yeah.
Thank you. All right. If you have points and games, what's the derivative of this function going to be measured in? Say again? Points per game. Let's see, what if you were measuring dollars over years? What's the derivative of this function going to be measured in? Dollars per year, right? And Leibniz might write this as like dp/dg for rate of change of points per game, or dt dollars per year. T is time, right? Does it seem okay? Do you want to ask a question on that? Is it too obvious? Or is it too complicated? All right. Some people think it's very, very obvious. Other people think it's a little complicated. And I want to make sure if you think it's complicated, you're telling me that. So right now, no one's telling me that yet? Okay. Let's see. All right, let's take a look at this. Katie Rayner, read for us.
Let n equals f of t be the total number of cans of cola Sean has consumed by age t, where the units of t are years. Interpret the following in practical terms. Include units.
I don't know what you're talking about. Mine says terms. You must have gotten a bad copy. All right. So f of 14 equals 400. I could have asked this in Algebra 2, I think. Kelly, you want to talk to me about it?
When he was 14 years, he had 400 cans of cola.
What does that mean? When he was 14 years, he had 400 cans of cola. No, but like he had it 400 cans of cola that year?
No, in total.
Total. Okay, so by age 14, we have consumed a total of 400 cans of soda. Is that reasonable? Yeah, I guess so. Probably didn't have soda like till he was what? 5. Let's say 4 because it's easy. So 10 years, about 400 cans, about 40 cans of soda a year. What's that? A can a week?
No, that's more than a can a week.
40 cans a year? Aren't there 50 weeks in a year?
Oh,
yeah. Okay. All right. No, not too bad. Yeah. This is true. All right. New question now. F prime of 12 equals 50. This is going to take a little bit of thought. David,
When he was 12,
age 12, he drank 50 cans of soda. Make sure you're.
yeah, wait, yeah,
I disagree.
but
Right. This is. I don't know if you can see, but there's.
yeah,
Okay. So that's as soon as you see that, it's a rate of change. So talk to me about what are the units of 50 going to be?
it's hands per year
Okay.
at year 12.
All right. So what's happening in his 12th year? David tells us 50 cans per year. So what is?
50 cans at that year is what I was attempting to say.
Yeah. I like it better the way I say it. 50 cans per year is what David was trying to say. What does that mean, Rachel?
He drinks an average of 50 cans per year.
No.
No.
True?
At that point in time, his rate of cans per year is 50 cans per year.
No. I want to make sure I'm getting it right. Sam?
Make sure he's getting it right first.
No, go ahead.
Okay, I was going to say that it was that at 12 he was drinking 50 cans per 12 years.
No. Let me try this and see if it goes over all right. At age 12, his consumption is increasing. Do you agree his consumption's increasing? This derivative is what? Slope. So a positive slope means consumption is increasing. How fast is it increasing? By 50 what? By 50 cans per year. So in other words, if he was drinking 100 cans last year, he's not drinking 50 cans this year. His consumption is increasing by 50 cans per year. So 150. No, we don't know. All we know is the slope. All we know is his rate of change. We don't know what he was drinking last year, but we know that it's increasing at a rate of 50 cans per year. So he's actually drinking 50 more cans than he was last year. All right, so adolescence hit, and he's drinking a lot more soda, right? Is that all right? Yeah, I know it wasn't, right? That was a lot harder than the first few, right? Oh, no. No, I wasn't asking from a health standpoint. All right, sorry. Is that okay conceptually? Do you see how that, tricked some of you? You wanted to just say 50 cans per year, but we're talking about the consumption increasing at 50 cans per year. Is that a little hard? That's hard a little bit. All right, let's take a look at another one maybe. All right, let's take a look at 12. Here we have total cost of paying off a loan borrowed at an annual interest rate of R%. Tell me this. When R goes up, when the percent goes up, what do you think is going to happen to the cost? It should go up, right? If you have a loan and you take it out at a higher percent, that means it's going to cost you more to pay it back. Does that make sense? Do people understand how, borrowing money works? You borrow money, you pay interest on the loan. The higher the interest rate, the more you end up having to pay back. Is that all right? Let's take a look at it. All right, what do we have? Using Leibniz notation, we should like A. What are the units for C prime, or the derivative, dc over dr? You want to take a shot at it, Rachel? Yeah, okay, so give me units. What do we measure cost in? Dollars. Per. Yeah, per percent. It does. dollars per percent. That's what this rate of change is. All right. What is the practical meaning? This is going to be hard. We're going to have to think about it. Of C prime, or the derivative of C at 5. What does that mean? What sort of rate are we talking about, Kelly? All right, so 5 is the percent. So we want to know, maybe I'll say, the rate of change of what? Of the dollars, the loan, the total costs. When what? When the rate is 5%.
Okay, I have a question.
Yeah, go ahead.
Why wouldn't we do it the same way as we did before when it was like at age 12, it was increasing by 50 cans per year?
So if we saw this, that would say when the rate is 5%, the cost is increasing at $100 per percent.
Okay.
So for every extra percent point, it's going to go up an extra $100. So it does say that. We just didn't get the other piece of it.
Okay.
Is that all right? All right, so what's the sign, algebraic sign of C prime of 5? You only have 2 choices. I guess you have 3. What's it going to be? No, algebraic sign. No, you can't go. Yeah, positive or negative? Positive? What's increasing? What's the function? The cost function. Does it make sense the higher the percent, the more the cost goes up? Yeah. So we have the cost function which goes up as percentage. That means the derivative is going to be positive. All right, so here's the thing. We started off saying this was obvious and got to the point where we had to think a little. Agreed? My guess is this. You'll either come back tomorrow saying, that homework was so easy, piece of cake, took me 5 minutes, or that homework really made me think, it took me like 30 or 40 minutes and it was only a few questions. One or the other. You tell me. All right, hey, have a terrific Tuesday. See you tomorrow.
Rachel, do we have global?
You're kind of